Hi, this is Bianca Bertolino, and this is the first lab, Charge Tapes, for Physics 2212. The purpose of this lab was to observe the transfer of electrons between surfaces to determine the excess charge on one piece of clear tape. We're learning how to model point charges by applying Coulomb's law and then simulating this interaction with Python coding in GlowScript. A preview of the main results was that the charged clear tape had a net positive charge, and the charge on the tape was found to be 8.605 times 10 to the negative 9, and the tape was efficient of 5.38 times 10 to the 10 electrons. The system of this experiment was the tape, while the surroundings was gravity, the desk, and everything else around us. The initial conditions were the clear tape and both tapes being approximately of equal length, and then the third piece of tape was attached to the desk. The first concept we need is Newton's second law, which states that the net force of an object equals mass times acceleration, and then we'll also need the gravitational force. We need these two to calculate the charge on the tapes. Then a charged particle creates an electric field, so we use the electric field formula and the relationship with the electric force in our calculations later on. Then Coulomb's law describes the electric force between two charged particles, factoring in distance and the charges of the particles. And then lastly, we're using superposition to find the charge distribution. Now let's talk about the experiment overview and procedure. So first off, the assumptions we made are that the tape is a point charge and it's located at the center of the tape, and that the U-tape has a singular point charge. Then we assume that tape A and B have equal charges, so we can apply superposition, and we also assume that there is equal distribution of charge along the tape length, and then we're ignoring air resistance. Now the procedure was to stick a base tape on our surface, so the desk, and we then got two pieces of U-tape that measured 20 centimeters by sticking those to the base tape. We then test the traction by hanging the U-tape vertically from the edge of our desk and holding our hand close to it. These were my measurements for the tape length, width, and mass, and the distance between the two U-tapes. And at the bottom you can see my calculation for the net charge Q on the tape. This is the first part of the code where I just input the measurements into the alter code, and then on the right we see the output where the red arrow is the electric force and the blue arrow is the gravitational force. So as conclusion we see that the forces on tape B are balanced. In the second part of the code we're trying to create a function for the electric field and trying to find the net electric force on tape B, and finding the gravitational and electric force on the right. We see that the output, and we know that these two forces are similar but not exactly equal to each other, which is likely due to the errors that we did during the experimental procedure. And some possible sources of errors were too inaccurate tape measurements, and the U-tape and the suspended tape were not exactly parallel, which resulted in an inaccurate separation distance. Lastly, let's go over some what if and what does it mean questions. The first question was, if we were to switch the charges, what will happen? So meaning that electrons were now positively charged and the protons were negatively charged, how will the observations about the tape change? And the answer to this is that there will be no change due to the physical conventions and properties of repulsion and attraction, and with the change in the charge, the electrical field will change as well. And the last question was, why were the computational values for Q different when we did a point charge model versus a line charge model? The line charge model accounts for the tape length and is therefore more accurate because there is a reduction of magnitude, meaning that the charge is distributed over a line and is further away from the point charge.